Hello, everyone. How's it going, everybody? Welcome to class. Come on in. Get started. I'm gonna have a little noise in the background. I got my nephews over, my nephew and my niece over, and they don't know how to keep their voice down. So a little bit of emergency. I apologize for any noise you hear. Hopefully they'll keep it down a little bit. Anybody have any questions before we get started?
Just to confirm, there was no lab last Thursday, correct?
That's correct. Yes. Yeah, I had a dislocated shoulder with my newly replaced shoulder. That was fun. Anything else? All right. Well, the last time I was looking back over our notes, the last time we had done a RL circuit, which is basically a circuit with a resistor and an inductor in it. And with that circuit, we basically considered what happened when you flip the switch to connect it to a battery. And what we saw is that the current sort of asymptotically approached some Imax or I0, whatever you want to call it. But basically what was going on was, as long as the current was changing, which is what happens when you first flip the switch and let the battery push some charge through it, then the inductor was acting like a back EMF, almost like a resistance. But as that resistance, or as that current got higher and higher, it started changing by a smaller and smaller amount each time. That's why it's asymptotic like that. And as that happened, it eventually came to such that there was no changing current, in which case the inductor just becomes a straight wire. And you end up getting a I0 or Imax just equal to V over R, where V is the voltage of the battery and R is the resistance of the wire plus the little resistor that's in there, but mainly just the resistor. So that was a neat finding. Now what we're going to do is consider the same scenario in reverse. So now we're going to imagine there's a current flowing already, and then we disconnect the battery. And as you might guess, since the battery or since a current's flowing, the inductor is still going to resist any change in flux. That's why they make them, right? So as the current tries to fall down, the inductor is going to try to create more current to fight that change in flux, and therefore it's going to slow it down to so it doesn't just instantly fall to zero. So that's what we're gonna see in this next derivation. So let's get started with that. So let's turn on my document cam real quick. Anybody, I had a couple more people come in since I said that. Does anybody have any questions before we get started on this last part of material, which is in chapter 30? If you're curious about where we're looking, we are basically starting off with, let's see if I can find something like it. Okay, yeah, so there's a derivation sort of like what I'm doing. What I did last time was sort of like the top half of page 791, and what I'm getting ready to do now is like the bottom half of page 791. So that's more or less what we're working on, okay? All right, so let's get started. So we have an initial current as let's call it I0. I think that's what I decided to call it. Yeah, I had an initial current I0, which we said from before was basically just the voltage divided by the resistance, the voltage of the battery divided by the resistance that was in the circuit. And that's because, as I said, once the change in current went to zero, then that made the inductor become basically just a straight piece of wire, or just a piece of wire. It had a coil in it, but without a changing flux, then that coil is only, marred by the fact that it's coiled up and has a longer length than normally would as a straight wire. So it doesn't act like a separate thing other than a wire. So in this case, we're going to have a scenario where we have, man, my light went off. Okay. Where we have a battery like this that was initially connected, and it had a switch connected to it. And of course, it was going through an inductor, which we draw like that, and a resistor, which we draw like that. Now, right here, we had a switch that was connected to that, but now we've moved that switch over to connect to this part of the wire. Okay, so this is where it's actually connected. And this is the instant that that switch is flipped, there's a current I0 in it. Okay, now if we write out basically Kirchhoff's loop rule, then what we'll get is L. Well, originally when we had the V0 or the V in here, we had V as a step up in current minus IR minus I, or excuse me, it's minus L di dt. And then we'd back to be back to zero. So it went up to V and then minus IR and then minus L di dt. That was the differential equation. But now we've got the same thing except V goes to zero. So you can actually write this now as L di dt plus IR is equal to zero. And we're even going to change that up a little bit. We're going to, in fact, go ahead and multiply through by 1 over L. And I'm going to put the IR on one side. So what I'm going to get is di over dt is equal to negative R over L times I. And now I'm going to take that I and put it under the di. So I'll get di over I is equal to negative R over L dt. And I integrate both sides. I'm going to integrate this from I0 to I of t. And I'm going to integrate this from t equals 0 to just plain t. Well, I think everybody knows that integral on the left pretty straightforwardly, right? So what I ultimately end up getting is the natural log of I of t. I'm just expressing this as a function of t. I'm not multiplying it by t. Over I0 is equal to negative, and here's another way of writing it, t divided by L over R. Because that L over R is defined to be the time constant for such a circuit. Now, if I raise both sides to the e power, or so I take this side and raise e to that power, and I take this side and raise e to that power, this side will just become I of t over I0. So I get I of t is equal to I0 times e to the negative t over tau. So what you can see is now I've got a current as a function of time that starts at I0, which in this case, if you hadn't done the previous problem, you wouldn't know it. It'd just be something that you'd measure. But if you realize the previous problem, that turned out to be just V over R. But the I0 will suffice here. And it's going to fall and exponentially decay. And in fact, because of the nature of E, if I go over to one time constant, tau equals L over R, this should be 0.37 I0. So that's how a RL or LR circuit behaves for a long period of time. Now, this is a good point since I've now done the charging up as well as the, or I say the charging up, but the developing of a current when we throw the switch to connect it to a battery. We did that last time, and now we've done the disconnecting the battery part. Now's a good time to work an example. So I'm going to do example 1. We're going to basically imagine a circuit like this without the battery connected yet. So I'm going to do, here's the battery. Here's the power source, the battery. And that has a voltage V equals 12.0 volts. And it's got a switch connected to it. And then from that switch, it runs to a resistor R. And that R is going to be 60 ohms. We'll call it 60.0 just so we'll have 3 sig figs. And then it's going to run through an inductor L and that inductance is going to be 240 millihenries. Okay. What I want to know is A, what is the current at t equals 0? B, what I want to know is what is the time constant? Remember, for a LR circuit, it's L over R. For a LC circuit, it's 1 over LC, and for an RC circuit, it's RC. So just to keep those in mind. So what is this? What is this? Part C, I would like to know. Trying to remember what. Oh yeah. I want to know what the I0 equals I max, whatever you want to call it, is. What is that? Okay. Part D, I want to know at what time is I equal to 1/2 I0. So that's part D. Let's say part E now. I would like to know the rate at which energy is delivered by the battery. So I'll put a question mark there. And then finally, I'll say part F. I want to know what is the power put into, and this is at T, such that I is equal to I0 over 2. And the same thing here, but I now want to know at what rate is power, or excuse me, at what rate is energy put in the B field when T equals T such that I equals 1/2 I0. And another student just came in. Let me let them in real quick. So let me scroll this pad up a little bit so you can see the whole question. So as you can tell, the whole question is, with that circuit, those parameters I gave you, what is the current at T equals 0? What is the time constant for that circuit? What is the asymptotically approaching current I0 or I max, whichever you want to call it? At what time is the current equal to 1/2 of that value? And then for part E, at that time, what is the rate at which which energy is delivered to the battery? And then again, at that same time, what is the rate at which energy is put into the B field? So let's start off by writing our solution. And I used the wrong pen. That one can't be erased at all. So luckily I didn't need any real erasure. But anyways, here we go. So I'll say solution. Part A. So what we got to realize is you're asking what's the current at T equals 0. As soon as you flip that switch at T equals 0, initially the current's still going to be 0 because it can't instantaneously jump up to I0, because the more rapidly it changes from 0 to something, the more pushback it gets from this inductor. So in fact, I of 0 is equal to 0 amps. Now that's an easy question. Now part B, what is tau? Well, tau is defined to be L over R, which is in fact 240 millihenries. Notice I'm leaving the milli on there, divided by 60.0 ohms. Remember I told you I'd add an extra digit just so we could have 3 sig figs. So, and I'm assuming that 240 has a decimal place right next to it, so that has 3 sig figs. So 240 divided by 60, I think y'all know that that is 4.00. And since I had a milli there, that becomes a millisecond. So the time constant really is 4 milliseconds. And that's a nice, easy calculation. Didn't even have to use my calculator. Now let's look at part C. So part C wanted to know what is I equals I0 equals I max. So I0 equals I max. What's going on there? Remember, the graph of this from last class was shown to be right here. And then it grew like this and was asymptotically approaching this value, which was basically as if this battery just had the battery, a wire, and then a resistor. Because as the changing current goes to 0, this part of the Kirchhoff loop rule, the LDIDT, goes to 0. So it's just like you have a regular circuit. You just have V equals IR. So this is, in fact, V over R. So that's what I max is. So they wanted us to calculate that. I'm going to go ahead and do that. That is V, which is 12.0 volts, over the resistance, which is 60.0 ohms. Now, if that was 120 divided by 60, I know it'd be 2. Well, the only difference is if I divided this by, or if I divided 2 by 10, I would get 12 over 60. So this is in fact 0.200 amps or 200 milliamps. Either of those are acceptable. Okay, any questions on that? All right, part D. So here's where we're going to make use of the equation that we derived last time. It says, at what time is I equal to 1/2 I0? Well, the equation that we derived last time was I is equal to V over R times 1 minus e to the negative t over tau. Y'all remember deriving that? So what we're trying to do is find the time such that this is 1/2 of that value. So I'm going to say 1/2 of V over R is equal to V over R times 1 minus e to the negative t over tau. You can see now that the V's over R's are going to cancel one another out. And because of that, you're going to get just 1/2 is equal to 1 minus e to the negative t over tau, which you can see is just e to the negative t over tau. So if I pull this side, it becomes positive, and then I pull this side, it becomes negative. It'd be 1 minus 1/2. Well, that's just 1/2. So I can take the ln of both sides, and that will give me negative t over tau is equal to the, notice it's the ln of 1, excuse me, notice it's the ln of 1/2, but that's the same thing as the negative of the ln of 2. So I'm going to say that's equal to negative ln 2. And the reason why is it automatically helps me cancel out that negative. And I also happen to know that this is 0.693. That's one of the, one of those numbers you just know from years of using it. So that's kind of helpful. So now I can see that t, the time at which this occurs, is actually equal to 0.693 times tau, which is 0.693 times 4.00 milliseconds, which gives me 2.77, if I remember correctly, 2.77 milliseconds. Okay. So that means I equals 1/2 I0. Okay, so that was part D. Does that make sense to everybody? There's a lot of different problems like this. I can just give you number after number after number with the voltages different and the currents different, or excuse me, and the resistances and inductors different, inductance different, and you just repeatedly solve these types of problems all day long. Now part E. Part E wants to know the rate at which energy is delivered by the battery. Well, when they say rate of energy delivered, they're talking about a power. And we already know what the power is for a battery. or for any circuit element, it's P equals IV, or you can substitute V equals IR in there to get rid of the V, then you get I squared R, or you can substitute V equals IR in there to get rid of the I, then you get I squared over V, weird stuff like that. But we're going to use just the P equals IV. So P by the battery is equal to the current delivered by the battery times the voltage of the battery. Well, the current delivered by the battery, remember this is at 1/2 I0. In other words, we're evaluating it at the time we just found, that 2.77 milliseconds. Okay, so we know that at 2.77 milliseconds, the current is not going to be 200 milliamps. It's going to be half of that. So it's going to be 0.100 amps. And the voltage, of course, is just the voltage of the battery, which is 12.0 volts. So we get that's 1.2 watts. And you can even say 1.20 watts if you wanted. So that's easy peasy. Now, the next part is a little more complicated. This, they want to know at that same time again, when the current is actually 0.100 amps, which is half of I0, at what rate is energy delivered to the magnetic field? Because remember, current carrying loop like this creates a magnetic field. So this inductor, being a curly loop of wire, as current goes through, it's going to make a magnetic field. And that's where the energy is being stored by this inductor. In the same way that energy is stored by a capacitor in an electric field, the inductor stores energy by a magnetic field. And in fact, we know that energy is 1/2 Li squared. That's one of the things we derived earlier. But we want to know the rate. Well, the rate is du dt. So that's the power that we're talking about. And that's power sub B, meaning in the B field. And I'll say at I equals 1/2 I0, just to remind us again, we're doing it at that particular point in time. Well, that's just d by dt of 1/2 Li squared. Using our chain rule, the derivative of this with respect to I would be 2 times 1/2 Li. So that's just going to be Li. And then you got to take the derivative of I with respect to t. So it's going to be equal to L di dt, right? Well, if you go back and look at our equation from when we had the battery, you can see that L di dt is just V minus IR. See, if I pull that over here, it's V minus IR. So I'm going to say now this is V minus IR, which is in fact 12.0 volts. Make sure I'm, oh, excuse me, Li di dt. Sorry about that. I said it, but I didn't write it. Everybody catch that? It's L di dt. So now it's going to be I. This part right here is L di dt from Kirchhoff's loop rule. Okay. Again, it came from that right there. If I solve for L di dt, that puts it on that side, puts the equal right there. You see it's V minus IR, but I had the I there already. So now what I'm going to do is say that power, I'm going to continue on this line. In other words, power is equal to the current, which is 0.100 amps.
We can't see.
Thank you. So this is P in the B field at I equals 1/2 I0. Okay, so there's the current part. Now I've got the V, which is 12.0 volts, minus IR, that's again 0.100 amps, times 60.0 ohms. I'll put this here. Now you can see 60 times 0.1 is just 6. So 12 minus 6 is just 6. And then 6 times 0.1 is 0.6. So I get 0.600 watts, which notice, by the way, happens to be exactly half of what we got for the power put out by the battery. Okay. So this is power into the B field. So any questions on that?
Thank you, sir.
Okay. So yeah, this is I think the hardest thing for me when I'm doing these problems is trying to make sense of all this when you go to do the Kirchhoff's loop rule. But what you got to remember, like in some cases, like when we do a capacitor, if you've already charged up the capacitor, then any loss in charge of the capacitor becomes a increase in current. So you have to do weird stuff like, okay, I took a battery, I charged up a capacitor in a RLC circuit or LRC circuit, right? And then I flipped the switch to take the battery out. Now the capacitor, since it's charged, is going to act like a source of power. So in that case, you've got I is actually negative dQ/dt. And that's sort of the hard part, or the part that's real easy to miss in making up these Kirchhoff loop rules. So I just warn you, that's the major part. So I would definitely advise you to read your book as it goes through each of these derivations so you can make some sense of all that. If you can't, you're not understanding the concepts well enough. But I suspect, you can do the concept questions. You're probably pretty close to being ready to roll. All right, so that was example one. I think that went okay. Now what I'm going to look at is I've got another problem we want to do, and we're going to do this one not so much as a problem. We're going to consider a LC circuit. We just did an LR circuit. Now I'm going to do an LC circuit, and what I want you to see is that when you get a capacitor and a inductor, you actually get an oscillation, not unlike you get for a harmonic oscillator problem. So let's do that. Oh, and I should write up here. I've been doing this lately. So I'm going to do, this is 11, 4, 21, and this is PHY242 D01B. So you'll notice these are labeled when you go to my Google Docs. They're labeled this way. You'll also notice, I want to tell you guys, when you look at the videos on my YouTube channel, they used to say PHY_242 _D01B underscore like chapter. I do it capital C or lowercase h, and then I do 29. And if I happen to have finished the chapter, I'd put fin. And then if I happen to start another chapter, I'd put S, T, and I'd put, say, 30 or something like that. And then I do an underscore and I put the date. Well, you can see the problem. It's a lot of crap to write. So I'm now writing just P242D01B. And I'm writing C lowercase and then 29. And if I use the F or the S, I just use the F like that. And then I put the date. Okay, so you'll see that as the name of the file, but you also see that as the second line in the description of the video. So that's how you can figure out what video you want to watch for a given day. All right, so now that I've got that, let's look at another scenario. And this scenario this time is going to be an LC oscillation. So this is an LC oscillation. Now we're assuming that, in your 241 class, you had covered 14, say, and 15, which is where we did the harmonic oscillator. So we're just going to assume that you know how to get those solutions. If not, you can look that up in your differential equations book, or you can look it back up in chapter 14 or 15 or any of that kind of stuff. But what we have in this scenario is we're going to imagine a charged capacitor. So there's a plus and a plus and a minus and a minus. And that charged capacitor runs into an inductor that doesn't like a changing current. And then it runs into a switch like so. And that runs this way. So this thing's initially charged up with a charge of Q0 over C. The charge is Q0, but the voltage is Q0 over C. So Kirchhoff's loop rule tells us that Q over C in general, that's Q of T as opposed to Q0 over C. Okay, but Q over C is a voltage increase from here to here, and then I go minus L di dt. And that's just, remember, L di dt is essentially Faraday's law. Okay, now there's no other elements in the circuit, so I've completed the loop, so the answer is 0. Now what I have to remember is I, in this case, is like I warned you earlier, negative dq dt. Okay, so now I can get Q over C plus L d2Q over dt squared is equal to 0. Or to make it more, I don't know, pretty, d2Q over dt squared plus 1 over LC, there's another time constant, times Q is equal to 0. So from our harmonic oscillator experience, again, now you see why we study so many springs, so many things act like springs. From our harmonic oscillator equation, we know a good hypothesis for this is Q of T is equal to some Q0 times cosine omega T plus phi. Now, if I go ahead and evaluate that by taking its derivative, taking its second derivative, and then plugging all of them in there, we'll get the what your math teacher called the characteristic equation. So I'm going to say dq dt. By the way, in physics, we normally just call that q dot. So that can save you a little writing. You just put a dot right over the q, and that's the same thing as dq dt. The derivative of cosine, of course, is negative sine. So I get a negative omega q0 sine omega t plus phi, and then q double dot, that's what you have when you do a second derivative. And of course, you see that gets really cumbersome once you start getting 4, 5, and 6 derivatives. But anyways, this is the derivative of this with respect to time. Derivative of sine is cosine, so I'm still going to get a negative, but now I got an omega squared q0, and I'm back to cosine, and I'm just going to leave it like that because I ran out of paper, but you know it's still omega t plus q plus phi. Okay, so now I can plug that back into this equation, and what I will get is negative omega squared q0 cosine omega t plus phi plus 1 over LC q0 cosine omega t plus phi equals 0, but that's also written as 1 over LC minus omega squared times q0 cosine omega t plus phi is equal to 0. Now this differential equation is the general equation from Kirchhoff's loop rule, so it has to be true at all times. And the only way that can be the case, you know, cosine is just going to wiggle back and forth between plus and minus q0. So the only way that can be true is this must be 0. So from that, we get that omega must be equal to 1 over the square root of LC. And in fact, omega is also equal to 2 pi f. So from that, we can say f is equal to 1 over 2 pi square root LC. And since f is 1 over the period, we can say that the period is equal to 2 pi square root LC. So those are all different values we can use. Now let's go ahead and graph this, and you're going to learn something really important here. Has anybody got far enough in electronics to hear of Eli the Iceman? You ever heard of that? Maybe even from your Navy background or something? Nope. Okay. Well, we're going to see why that's the case. Okay. Eli the Iceman. So what I have now is a plot of Q versus time. Okay. Now, Q is not normally something you deal with in a circuit. You normally deal with voltage, but remember, voltage is actually Q of the capacitor divided by C. So if I want at least the voltage of the capacitor, I just take this Q and divide it by C. So what I see is that Q is equal to Q0. So there's a Q0 there. And assuming phi is 0, then it looks just like this. Now you'd have to do some initial conditions and all that stuff to find out really what phi is, and as well as what Q0 is. But you can see where Q0 came from already, so that's why I just went ahead and wrote it in there. But if we assume that phi is 0, whatever it is, we're still going to graph it as if Q is 0, as if phi is 0, but it would still be the same graph staggered by the exact same amount compared to the current. That's the main thing. So what I see here is just a straight cosine curve. And again, it's going to come down here to negative Q0. So this is the period T, which is equal to 2 pi times the square root LC. So that's how long it'll take to complete one cycle from a peak to 0 to a peak again. Okay. Now, what I want you to see is if I plot the voltage, so now I can do the same graph. So this is V cap. So the voltage across the capacitor is going to be this with a peak at Q0 over C, and the negative peak at negative Q0 over C. So notice Q0 over C has units of voltage and all that good stuff, but it's the exact same curve. It's the cosine curve. Okay. Again, this is T equals 2 pi times the square root of LC. Now, the big point is I want to make a similar graph right here where it's the current. So I want to compare the current and the voltage. That's why I'm drawing this graph directly above the other one, or directly below the other one, excuse me. So now I'm going to do like this. The amplitudes don't matter, but where the amplitudes happen do matter. So what I'm going to do is come down and draw this line just to keep me straight, this line to keep me straight, this line to keep me straight, this line to keep me straight, and that should be good. Now, I is negative dq dt, which we can see dq dt was this, so it's going to become positive this. So it'll be omega q0 sine omega t plus phi. And we already decided we were going to treat phi as if it's 0. Again, if it didn't, this would shift over by an amount phi, and this would shift over by the same amount phi, so we'd still get the same results. That's the main thing I'm trying to say here. So this is just a positive sine wave. So what we're going to do is say, okay, this is omega q0, which is really I0. So this is going to come up, reach a max, reach a 0, reach a min, and then back to 0 at t equals 2 pi square root LC. So this is the current, and this is the voltage. And what we say is V peaks at t equals 0 seconds. But here we say I peaks at t equals 1/4 the period. So this one peaks, and then you got to wait some time, and this one peaks. That's where we get Eli, the Iceman. We don't get the Iceman part yet, or the part. We just got the Eli, and that means voltage is ahead of current in an inductor. Remember, the symbol for an inductor is L. So, and you see it's 90 degrees, and that's exactly the fact. Okay. In fact, they even call the reactance, which is sort of like resistance that has units of ohms, but they usually use a X for it. They say the reactance, if you take a more advanced course, they'll say the reactance is I times omega L, which, if you know about graphing in the polar, I mean in a coordinate where the vertical axis is the imaginary axis, that would mean you're ahead 90 degrees. So they'd plot the omega L, or the resistance, if you will, for the inductor would be plotted on the vertical axis out in front of the horizontal axis, which is your voltage. And then not only that, it turns out that that's for an inductor. For a capacitor, you end up getting, basically they do 1 over omega C, but it's really negative I over omega C. And that puts it behind by 90 degrees. So that's why Iceman comes in. Your book just calls it omega L and 1 over omega C. Okay. But like I said, these X's do have units of ohms. Okay. Any questions on that weirdness? Okay. So that's sort of an example, but it's really more of a derivation, and it's to make some sense of what we found. Now, the other part that we're going to do is the whole kit and caboodle, if you will. We're going to now attack an LRC circuit. So let's look at an LRC circuit. Now, again, we get to be, we're a little bit fortunate because in principle, we've already studied the harmonic oscillator. So I can write out the equation and all things look really great. I'm going to go ahead and draw the circuit right here. I'm going to say it's this this capacitor is already charged. And I'm going to say it's connected to a resistance R. And that's connected to an inductance L. And then over here, we run into a little switch mechanism. And the wire comes back and sort of evidently misses the middle because I'm a goober. Okay. So in this case, what you see is I'm going to go up a voltage amount using Kirchhoff's loop rule. I'm going to go up an amount of voltage that's equal to Q over C. So I'll say Q over C, and then I'm going to go minus IR, and then I'm going to go minus L di dt, and that's equal to 0. But since I, again, is negative dq dt, we can combine these two to get, in fact, L d2q over dt squared plus R dq dt plus 1 over C Q, and that's all equal to 0. So that's our typical harmonic oscillator equation. We had here M d2x over dt squared plus B dx over dt, because that was the dampening due to air resistance, which is proportional to the velocity, plus k times x, which was basically on the other side, it would have been a negative kx, which is in fact, dang it, what's his law? Newton's nemesis, Hooke's law, sorry. Okay. Drew a blank there for a second. So you can see it's the exact same equation. The only thing that's happened is we're replacing the C, 1 over C with a K, the R with a B, or I should say a K with a 1 over C, a B with an R, and an M with an L. So it turns out all that solution is just a normal rigmarole. And in fact, I did take the time to derive it properly. The big thing about the harmonic oscillator problem, and people usually forget this, is when you go to solve this, you again assume a characteristic equation. So what I'm going to do is go ahead and divide through by L, and I'll say d2q over dt squared plus, dividing by L, I get R over L dq dt. And then again, dividing by L, I get 1 over LC Q. All that's equal to 0. I'm going to say let Q equal to some constant A times e to the rho t. Okay. That's the big deal. When you find a linear equation with constant coefficients like this, no matter what order, this solution always works. But as you can tell, in a second order equation, we're supposed to have two roots. You'll see in a second what that makes it a second order equation. And therefore, you're supposed to have them. But there's a part that people usually miss, and I'm going to go ahead and show you that too. So let's now take this and compute Q dot. Again, I'm trying to save some writing time. So Q dot is just going to be A rho e to the rho t. And then Q double dot, which is dq dt, dq dt. In other words, the second derivative with respect to time. That's just going to be A rho squared e to the rho t. Now I put all that in and make what we call the characteristic equation. That's going to be rho squared plus r over L rho. Notice I'm not writing the A e to the rho t. You'll see why in a second. Plus 1 over LC. All of this times A e to the rho t equals 0. That's the characteristic equation of this little part right here. Remember, this has to be true. This is Kirchhoff's loop rule. It has to be true at all times. So the only way you can make that happen is by making all this equal to 0. So now I've got rho squared plus r over L rho plus 1 over LC is equal to 0. That tells us that rho is equal to negative r over L plus or minus the square root of r over L squared minus 4 times 1 times 1 over LC. I'm using the quadratic formula, right? All that over 2a, which would just be 2 because the coefficient's 1. So this breaks itself up into some very natural points. It's going to be negative r over 2l plus r minus. Now I'm going to do square root, and I'm going to suck that 2 inside by squaring it. So I'm going to say it's r squared over 4l squared minus, now when the 4 goes over here, it's going to cancel out with this 4. So this is just going to be minus 1 over LC. Well, in the case of this stuff under here being a negative, then this is going to become I times positive I times this and negative I times this. But in the case of this being positive, it's going to be plus this and minus this. But in the case of this being 0, that screws everything up because the way you're supposed to have it is two independent solutions. So it actually is independent, two independent solutions when you use the plus 1 and the minus 1. You just change the Q. Instead of it being A e to the rho t, it'd be A e to the rho 1t plus B e to the rho 2t. So long as the rho 1 and rho 2 are in some sense what they call linearly independent, then that works. So those all work as long as this isn't 0. When this is 0, though, and this is the part everybody forgets, then you have to say, oh, well, this is a twice repeated root. In other words, it's a perfect square. And since it's a twice repeated root, you actually have to multiply it. Since it's twice repeated, you got to multiply it by 1 or some constant a plus some other constant x to the 1 power. And if it was 3 times, it would have been plus some eighth to x squared, and so on and so forth. So any questions about that? All right, so what we end up getting is 3 cases. Let's say 4 r squared over 4 L squared greater than 1 over LC, which is the same thing, by the way, as r squared being greater than
We can't see.
4L over C. Thank you. Okay, so in other words, I'm parsing out whether this is positive, negative, or 0. So I can multiply this side by 4L squared. That'd be 4L squared over LC. So this should be 4L over C. In that case, we get Q is equal to A e to the rho 1t plus B e to the rho 2t, where rho 1 is equal to negative R over 2L plus square root blah, 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 and rho 2 is negative R over 2L minus square root blah, blah, blah. Okay, so that's one case. And that turns out to be basically, and I wrote this to make sure I didn't speak it incorrectly. Yeah, this is the overdamp case. Because it really, notice without the I up there, the e to the t is just an exponential decay thing. So these are just two exponential decays. So it's overly damped. It's just going to go, it's never even going to oscillate. It's just going to go like that, right? And then there's another case for R squared over 4L squared is less than 1 over LC, which means R squared is less than 4L over C. Well, in that case, we get Q is equal to A e to the rho 1t plus B e to the rho 2t. But in this case, let's call them prime just to keep them from getting confused. In this case, rho 1 is equal to negative R over 2L times plus I square root of 1 over LC minus R squared over 4L squared, like that. And then rho 2 prime is the same thing, but minus I square root and negative R over 2L. The deal is when you have e to an I, then you actually can make sines and cosines because of this. E to the I theta is equal to cosine theta plus I sine theta. Because of that, and you can do that by a Taylor series if you ever want to prove it to yourself. But in doing that, you can see that ultimately you end up getting sines and cosines for this. And that is the case that we call underdamped or just plain damped. So this is underdamped is what we normally call it. But sometimes mathematicians will call it damped. And the equation in that case, or the graph in that case, looks something like this, where it actually oscillates back and forth. This one just looks like, you know, like that. Whereas this one looks like that thing. And then the final case, and this is why I'm doing this, is because people always forget it, for R squared over 4L squared equals 1 over LC, which is the same thing as R squared equals 4L over C, which is obviously a very rare case. Then you have to say that Q is equal to, now this is a root, a single root that you're getting for the answer. You're only getting R over 2L, or negative R over 2L. So when you have a single root, the methods of differential equations teach you that you have to take A plus B x to the, since it was 2 root, it's supposed to be 2 minus 1, which would be x to the 1 power. If it was 14 roots, it would be up to x to the 3rd. So I just take this and now I multiply it by e to the negative R over 2L times t. That's the whole function. And that, in fact, is the critically damped. Okay, so that's the critically damped we normally talk about. I'm sorry these words got so small, but I think you see the 3 breakdowns of what it becomes. Any questions on that? All right, so we actually have a solution. And in fact, if you added a voltage source, all you have to do, a power source, is put that on this side. And the theory of linear differential equations basically says that when you have a function on this side, you take one solution that fits with that and just add the solution as it fits with a 0 on there, and you're golden. So you don't even have to mess with that. But now we've got that out of the way, and we can try some more examples. So nobody has any questions on that, correct?
Negative.
Hold on a second, class, just for a second, please. I'm back. My niece and nephew are out there. I got the TV so loud, I was afraid it was going to make it where y'all couldn't hear me. So we've now done all the cases of the different LRC circuits, and we basically know how it's going to behave. And we see that when you combine a capacitor and a charge capacitor, that is, and a inductor, then you're going to get a actual relationship that shows that the current oscillates back and forth in time. Your book also handles a case for AC circuits with an AC source. And in that case, like I told you before, they're going to do something called the inductive reactance. So again, I said the inductive reactance is X sub L, and they're just calling it omega L. Like I said, more advanced courses will call it X sub L is equal to, actually they'll use a J, by the way. That's what they use in electronics, is a J instead of an I. And that's because they use lowercase I for current sometimes. They introduced this, but again, it has units of ohms. So it's in units of ohms. And they also introduce a capacitive reactance. And that's X sub C. And I'm trying to make sure I'm using the right nomenclature. They use, that's usually written as 1 over omega C. But again, like I said, more advanced classes, and it's sort of not, it's actually even less advanced to use it this way, because it's just making you use the imaginary axis to understand sinusoidal voltage. In other words, to understand DC or AC current, but it would just be negative I over omega C, because what you do as a technician and an engineer, a lot of times the easiest way to think about electricity is think about it this way, where you have voltage here and you have the imaginary axis here. So this is the imaginary. And what's going on is you have what's called a phasor. So this is a phasor diagram. And that represents the peak voltage, say, which is what, 125 times the square root of 2. Anybody remember that number off the top of your head? 125 times the square root of 2.
$176.7.
Thank you. About 176. So what they do is they actually imagine something that long, and it's actually spinning in space. So right here, it's 176 volts. But when it gets to 90 degrees, it's I. Right? It's 176 I. And then when it gets over here, it's negative 176. And since it's I, of course, that's 0. It has no real part. It's just imaginary. And then it gets around here and does that. And all of this, of course, this theta is equal to omega t, where F is equal to 1/60th of a second. And of course, omega is equal to 2 pi F. So by thinking about it that way, they can just sort of picture it as that. But when you go to do this kind of circuit, like you take a series RLC circuit, if you want to calculate the reactance and what the voltage is going to lead the current by or lag behind, you have to use all these values. So with that in mind, let me show you, we have a whole new set of equations. With this, we have R sub L is equal to, just like V equals IR, this thing plays a role of a resistance. So R sub L would be I times X sub L, and R sub C would be I times X sub C. And then the total resistance, Z, is actually a weird thing that turns out to be this square of R squared plus X sub L minus X sub C, excuse me, I got ready to square it first. X sub L minus X sub C quantity squared. And that's sort of your thing that really limits your voltage, not the current itself, but all that junk. So let me show you an example, and maybe that'll set it straight. Yeah, it looks like I got 15 minutes. Looks like we're going to do it. Okay. I want to try to find a problem like I want to do. I have one written up with some numbers, but I'm kind of worried about those numbers right now. So I'm looking basically at section 30-8, which is the LRC AC circuit. Yes, that would do nicely. So let's suppose we have a resistance equal to 30 ohms. So this is example 2. We got R equals 30.0 ohms. Let's say we have an inductance equals 60.0 millihenries. And let's say we have a capacitance of, let's say, I like to keep all these multiples of each other so it works out kind of nicely. So let's say this is going to be 15.0 microfarads. Okay. And they're connected in series to a 90 volt I'm not going to say 90 volt, to a 120 volt AC source. So a voltage supply or whatever you want, okay? And it has a frequency of, I'm not going to do the boring 60 hertz. I'm going to go ahead and do 600 hertz. What I'd like to know is, A, what is the current? B, I'd like to know the voltmeter readings across each element. And then part C, I would like to know the phase angle, which you're going to see what that means in a second. And D, I would like to know the power dissipated in the circuit. Okay, so there's our setup. We got a regular circuit. What we're going to do is one by one just calculate these things. So first we need to find the reactance for the inductor and the capacitor. So first off, let's start this way. And I think I'll switch back to black just to stand it off a little bit. So A, in order to find what is the current, I really have to know, if you were doing a regular DC circuit, for instance, you'd have to find the total resistance, and then you take the total voltage divided by the total resistance, and that would give you the current. Well, that's the same thing we're doing here. So what I got to do is find out what the XL is. And remember, XL is in fact omega L. And omega, of course, is 2 pi times F. So I got 2 pi F times L. So I'm going to say 2 pi times the frequency I said was 600 hertz. And then the L I said was 60.0 times 10 to the negative third henries. So I'm not messing with any millis on this thing. I'm just going to leave it all as pure base units or whatever. So I'm going to say 2 times 3.14159. Actually, it takes me less time to punch that than it does to push my pi key, times 600 times 60 e to the negative 3. So y'all can see what I wrote there. 2 times 3.14159 times 600 times 60 times 10 to the negative 3. And that's going to give me 226.2. That's extra sig fig, and that's ohms. Now I'm going to say the capacitive reactance, which is 1 over omega c. And notice, by the way, the larger the frequency, the bigger the capacitor or the inductive reactance gets. So an inductor actually, for high frequency, basically acts like an open circuit. Whereas for a capacitor, when the frequency gets really, really high, then the capacitor acts like just a plain wire, like it doesn't resist at all, because as this goes to infinity, the resistance goes to 0, basically. So you have the little resistance of the wire, and that's basically it. So in this case, I'm going to say 1 over 2 pi times F times C. So that's 1 divided by 2 times pi times 600 hertz times 15.0 times 10 to the negative 6 farads. So all these units, just by the way, work out such that it's ohms. You should probably try it on your own at some point. But I'm going to say 1 divided by, I'm going to say 1 divided by parentheses 2 times 3.14159 times 600 times 15 e to the negative 6. So y'all can see what I did again. 1 divided by parentheses 2 times pi times 600 times 15 times 10 to the negative 6. That gives me 17.68 ohms. Again, I'm carrying 1 extra sig fig. So if I want to know the current, then what I have to know is I've got to now take these XLs and realize that the total impedance Z is equal to the square root of R squared. I did write that earlier, didn't I? Yeah, I was making sure I put the R squared. R squared plus XL minus XC. Quantity squared square root. So in this case, I take the square root of, now the R we found was 30.0 ohms. So that's a little more effective than the capacitor. I'm going to square that, plus 226.2 minus 17.68. Both of these are ohms. And that's going to be squared. So now I'm going to try to calculate that. Okay, all of a sudden my calculator decided it's going to crash. Oh, I guess his battery's dead. Ain't that nice and helpful? Okay. I have a backup calculator. It's my phone. Oh, there it is. That was scary. Okay, so you guys back up your back up my calculations here, because this thing, this calculator I'm using is not very friendly regarding fat fingers. So I'm going to take now and say 30 squared plus, darn it. So 30 squared again. Now I'm going to say 226.2 minus 17.68. Notice that cuts it down to 1 decimal place, but that's still 4 sig figs, which should be rounded to 3, because the fourth sig figs in a slot that was non-significant. Ah, crap. So I got 900 when I squared that. Now I'll say 226.2 minus 17.68 minus, now I'm going to square that. Now I'm going to add those two. So I got 43,480 and I'm adding it to 900. Now I'm going to take the square root of all that. And I get 210.6, actually 0.7 ohms. Now the deal is the IRMS, the IRMS times the Z gives me the VRMS. Of course, it also works out that if I use I peak, then this comes out in I peak. But what I want is the current. That's what part A was asking for. So I RMS, and again, the 120 volts I used were supposed to be RMS. I'll just put that note there to remind you. So IRMS should be 120 volts divided by 210.7 ohms. So I get 0.5696 amps, or about 570 milliamps is how much current we got going through there. Everybody see how we did that? Now, what does that stupid R thing really mean? So what does that actually mean? So you might have noticed it looks like a Pythagorean theorem and stuff like that. Well, what it means is this. Remember that graph I told you where you can put the imaginary axis up here and then the voltage over here? Well, the root mean square voltage is what we're using here. So you're imagining basically the voltage here to be 120. And that actually happens to be the same axis that the current or the voltage across the resistor is on. So in this case, I got VR is the voltage of the resistor, right? And then in front of that, I have the voltage across the inductor, which is, this is of course I times R. And then over here, I have I times XL because the current leads the voltage in inductor. And then this way, I mean, the voltage leads the current in an inductor. And this way, I've got an I times XC. So you can see that basically the phasor we're looking for is a triangle, or is the diagonal of this guy. And obviously this guy's length from here to here is XL minus XC. So this is XL minus XC, and this is just R. It's technically I times that, and it's technically I times that, but you can see now why it comes out to a Pythagorean theorem, and that's the phasor. And in fact, this angle right here is the phase angle that they're talking about. So when they ask for the phase angle, they're asking for that, which you can just basically take the inverse tangent of the difference in the capacitance and the reactance for the inductor. You can take that, and then opposite over adjacent. Adjacent is R, so you do inverse tangent of XL minus XC over X over R. Now, I've got part A. Now, part B wants to know voltmeter readings across each. Well, part B, the voltmeter reading V for the resistance is equal to 570 milliamps times 30.0 ohms. So that's going to give you a certain number of, if I left the milli in there, then it would give you millivolts. But in this case, I'm going to do times 30. So I get 17. If this was 0.570 times 30, that would actually give me 17.09 amps, or excuse me, volts. But I did convert this to do 1709. I did convert this to amps. So I use 0.570 amps instead of milliamps. Just put that there to clarify. So that's how many voltage would be across that. VL would be again 0.570 amps times the X of L, which is 226.2. So 226.2, multiply that, that gives me 128.9 or 0.8 volts. And then V sub C, 0.570 amps times, this one was 17.68. So 17.68. And that gives me 10.07 volts. So that's the voltage across each of those. Anybody have any questions on how we did that? Okay, so the other parts, or that's part B. Part C is, oh, the phase angle. Okay, so the phase angle for part C, the phase angle phi is equal to the tangent inverse of 226.2 minus 17 point, thank you, minus 17.68 ohms over, and then of course the resistance is just 60, or is just 30 ohms. So I should be able to take 226.2, 17.68 minus, and then I divide that by 30. So I get 6.95 is what I'm taking the inverse tangent of. So I take tangent inverse. .81 degrees. So basically that just shows you how much bigger a difference the inductor makes compared to the resistor. Notice that's 226 ohms versus 30 ohms. So yeah, it's very near 90 degrees. The inductive part of this is the major part of the circuit. So that's the phase angle. Part D, they want to know the power dissipated. And the power dissipated, you can actually just work out from P equals IV. So D, you can use P equals IRMS, VRMS times the cosine of the phase angle. That's something, again, that's kind of neat. But really what we're finding out here is the part that's in the real axis. That's why we take the cosine of phi from this diagram. Take the cosine of phi, you just get the real part. So that's why that's that way. So I'm going to take the IRMS, which is 0.570, actually 0.5696, carry extra digit, in other words, 0.5696 amps times 120 volts times the cosine of 81.81 degrees. And when I do that, I'm going to get and 0.5 5696. And that gives me 9.734.
Can you move it up?
Yes, 9.734 watts. I am skipping the impedance matching and the three-phase AC, but I do recommend you read it if you're going into double E. If you're not going into double E, it's not that helpful, but it is informative to let you know, for instance, how voltage is actually delivered at houses in America. We use that triphasic stuff where they're out of phase by 60 degrees on each leg, so that you can put two of them across and not have to actually carry 240, but the difference between two of them, because their phase differences, gives you a 240 some volts. So that's kind of neat, but that's it. And we ran over by about 4 minutes. I apologize for that. Of course, you know, always if we run out over, you're welcome to leave. The recording's still running, so nothing bad will happen. You'll still be able to catch up with it. But I appreciate you coming, and I will wait for the last of you to leave in case you have any questions.
And just to clarify on the recording, should we just go straight to your YouTube channel, or will
Yeah, I'm
they
not putting them
eventually-
on the canvas anymore. It takes so long to do that. So
Okay.
yeah, just do that. And I did recently update the list last night. So if you look in that useful documents, one, I put equation sheets there, and two, I put the latest, which was November, I think 3rd. I put up the last videos, so you should be able to see everything there.
All right, thank you, Professor.
No
Thank
problem.
you.
You have a good one, everybody.
And lab is on today, like normal.
Yes,
Okay. Thank you.
no problem. Anyone else? William or Kendrick? All right, we're out of here then.
You know what?